a sec here.
All right. Well, great. Thanks, Jason. And in conclusion, since he summarized it, we got that. That's the whole message. But I'll try and this is a very complicated subject that's got some very simple ways to talk about it. I'll try and err on the simple side, but not too much, and avoid give you enough of the complexity to see what we have and where we're going. If I'm too much on one side or the other, just raise your hand or shout out and let me know that I should go lighter or deeper. We'll try and do that. So my name is Tom Hudson, as Jason said. My background is 25 years with the IBM company. I was fortunate to spend a lot of time in the growth of this industry, and since then I ran a number of the divisions for IBM. I started as a logic designer, came up through the ranks, and was a software guy and ran the software business for a while. Then I ran the hardware business. One of the things about logic designers is you make big things small, right? And we're still trying to do that across the industry. We've sometimes surprised ourselves at just how good we've gotten at it. One of the things you'll see here is that artificial intelligence is pushing Moore's law. And it's not really a law, as all of you know. It's just kind of a statement of where the industry was going, but we're exceeding the capacity to grow with the demands that AI is putting on it. And we think we might have a solution to that by doing something very different, very orthogonal to the way computing for AI and machine learning is done today. So the corporation here is RISC AI. You can find this under RISC.ai. And we have we're taking a lot of research and development from two different companies, Modal Technology here in Minnesota and Taco here in Minnesota. Modal Technology has had technology in the set theory and interval modal arithmetic. And that's what we're going to talk about, where we bring that to the market. We'll be the first to market with that. Today, there is no computer on the planet that does interval modal arithmetic. We're going to change that. We can do it today in emulation mode using the ALiX software that was referred to. And we've proven that its benefit and value in the marketplace today already, and I'll share a little bit of that with you. We're going to then take the benefit of Taco that has lots of experience. My two partners here from Tom and James from Taco have lots of experience producing ASICs and integrated circuits and designing those. And we're going to use their assistance along with the likes of what's changed in the industry to allow us to go to a chip. And we'll put that interval modal arithmetic mathematics into a chip. As an ASIC, we'll then put that into a package, into a board, into a 1U high, into a rack that we believe will compete with the fastest things on the globe, and making it even faster, cheaper, and actually more explicit with the answers you get. A lot of what you hear today in AI is based on a starting guess, reiterating on that guess, lots and lots of times, and using the power of the computer to do it faster than you and I can do it, and hoping that that guess gets you an answer, but it's often not a repeatable answer because you started with a guess, and depending upon where you started, you get a different answer. We're going to change that too, so we can give you an explicit, discernible answer. So that's the background, that's the punchline. I'm going to try and move to the next slide if I can here. Let me see. So we will be the first to market, RISC. That's a name that most of you are probably familiar with. It stands for Reduced Instruction Set Computing versus CISC, which is Complex Instruction Set Computing, which most computers do today. The whole idea is that we will bring this first to market with the combination of both software that works today and then be migrated onto an ASIC that will work in the future. Let's call it 18 months on an ASIC, probably about 1 million times or more faster than it does today with the software. That's important, but that's not where we're stopping. We're looking to make that scale even much further. So we raised some seed capital to get us going. We're looking to raise further monies to allow us to do a chip. and to solve what we think are some of the major problems in artificial intelligence and machine learning today. We'll do it, we believe, faster. We'll do it with a definitive answer. It won't be the black box answer that you typically hear of. In fact, the CEO of Google was just quoted about that on 60 Minutes, if you saw that, how much of it's a black box. And that's what's got some scariness to AI today. We think we can take some of that away, maybe it all away. I'm going to try and avoid hyperboles because there's an awful lot out there in the industry to start off with. We think we can deliver an explanation with that software that takes away the black boxness. We think we will save energy because it'll require less computer power to do it. We'll also introduce with the computer chip, what these two gentlemen can do is a thing called quasi-adiabatic, which means less heat, less energy running on the chip itself. And so those two things together, we think will give us world-class capability. And then, of course, we'll do it in less time. This technology has really been in the making for over 10 years. And it was not ready until really now. And the industry, frankly, wasn't really ready. What we needed was, we didn't want to go build a whole architecture. So RISC-V has come along as an industry accepted architecture that breaks the stranglehold that an Intel or an NVIDIA or an IBM have on the marketplace with their architectures. You've all heard of the x86 and the Pentium and all the generations following that. Well, they don't share that with anybody. They don't open it up to allow you to do anything with it. We needed to open it up to put this new instruction set in it. RISC-V allows you to do that. And it's built around that capability. So we can just license that and use it. We can also do something that didn't exist in the industry maybe 10 years ago. We don't have to build a foundry to make the chip. We can go to a global foundry or others like them who have the capacity to take our design, our electronic automation designs, take it into what they call a tape out. I don't think they use tapes anymore to do it, but and then that feeds into the silicon factory to basically etch the wafer, which today are typically 12-inch size wafers or slices of silicon, and to create in a 2-month cooking process, if you will, a new chip to our specifications. On the RISC-V architecture, we'll run that with a Linux operating system, so we don't have to write a whole new operating system. We can run our application, ALiX, on Linux, on the new chip, on the RISC-V architecture. Okay, so that's how this all comes together, at least in our mind's eye. We have this patented. Between hardware and software, we have nearly 58 patents that are granted and a number pending. I'll be the last guy in the world to say you can stand behind your patents, but we think we can stand behind the patents pretty well. And they're pretty broad patents to allow us to do this. We have recently raised some money to allow us to go forward, and we're in the process of raising an additional $30 million to actually go to production with the chip and to go to market with those computer systems, okay, over the next 2 years. We're a pretty senior team, and I like that. My experience since IBM was to build other companies in high-tech applications, either new technology against old applications or old technology with new technology against some new applications. And I've done that in communications, in storage area networking, and SAN over WAN technology that's been used basically by, we started with nothing and basically implemented that across virtually every Fortune 500 company on the planet. So that's literally was the top 783 companies, 44,000 network implementations. Took that company public, merged it with McData and Brocade, merged it again with Broadcom, which still exists today. Done a similar thing with a evaluated networking company to do very, very high-speed computing. At the time, 1 billion bits a second and faster communications. This was in the early 2000s. Then did another company, did software, connecting any software to anything. That was merged with another company called Kofax. Have a parking company going, have a smart clean cube operating room company going, have put good senior management in place to run those, and it let me go off to do something else new. I'm a lousy golfer, and I really a worse couch potato. So I've got a bunch of kids, and I love to teach them to ski on water and snow. But other than that, I like to do this kind of stuff. So what's wrong in the industry today? Well, the industry leaders, among others here, Ron Black and Jeff Hinton, formerly of just Google, you might have read, would say that scaling is failing. And I think that kind of encapsulates it. To date, most people have been throwing more and more computer power, more teraflops, trillion floating point operations per second, at whatever AI and machine learning problem they have. They know where they can buy it. NVIDIA and Intel and others are happy to provide it at hundreds of thousands to hundreds of millions to billions of dollars at a crunch. The latest one was, I think you might have seen in the headlines, $10 billion purchase of NVIDIA product to run the Microsoft AI website. And they're just beginning. That was this year, right? So, but it's failing in the sense that it's not giving you the bang for the buck. In business terms, I would say it's a diminishing return. You can throw $1 million at it and you don't get $1 million of return back. You get a more marginal return. So that asymptotic curve that you see there is more and more computer power, teraflops growing to petaflops, thousands of trillions of floating point operations per second is where we're headed. The size of neural networks has outgrown this capacity. Instead of having a small neural network, you get a more complex neural network with a lot of what they call hidden layers. And those hidden layers cost money, cost power, cost research time. We think we can simplify that because set theory mathematics allows you to go to as little as one layer, okay, which is pretty revolutionary. So that's where we look to address this problem across the industry. I know that it's big. The industry is enormous. You figure out how you measure it, but it's hundreds of billions to, some would say it's going to be into the multiple trillions by the end of the decade. In either case, we'd like to get our fair share of a slice of that. This market is huge, but people are throwing lots of money at it. You almost can't open the paper or listen to the news these days if you still read papers that talk about computer power and the money being spent on AI. I think it's vast. And everyone wants a new and a faster chip. And they're usually focused on the performance that they can buy from that chip. And true, the asymptotic curves of price performance have been improving, either cost going down or performance going up for the last 50 years since I was a kid. Right? And I've got to live that. But the fact is that two sets of cost reduction and performance improvement are actually falling behind the demand by AI to satisfy those equations. Things like the large language model that is part of the ChatGPT. It has a binary code for every word in the English language, the Japanese language, the Chinese language, and every other language you can think of. That's a big database. Well, how about a bigger one? Weather. How about a bigger one? The genome. People are only slicing at pieces of that today. No one's really been able to digest the whole thing. We think we can start to do that. When you think about AI, it falls in, and I'm not an AI expert, I will tell you that. I think I can solve some of the problems that they need, but I'm not an AI expert. Pretty soon, one of my kids or grandkids are going to show me how they are as they come out of Purdue University with a AI degree, right? That I'm hoping is worth the money it's spent. In AI, there are three areas. Training. How do you train someone? Is it a dog or a cat? Real simple. Well, maybe not so simple. Then when you explain it, how do you know why did you say it was a dog or a cat? That's not done well, if at all, today. And then what's the inference? Well, how do I know a new thing shown to the same engine is it a dog or a cat, right? That's where the power and result is, really to show results and value. Because training is cost. Show 1,000 pictures of a dog that you know are a dog. The computer pretty soon starts to understand, well, that's a dog, and here's the 1,000 ways it could shape and be different. Until you show it a dog with no hair. Well, is that a dog or a cat? And then you show it some cats to say that's not a dog. And then you show it something new. So you finish the training, and if you now show it the first new thing, I don't know if it's a cat or a dog, do you? Well, based on those inputs and the training, it will tell you if it's a cat or dog. That's the basics of computerized training. And it's doing that with ones and zeros, by the way, right? It's doing that with lots of images, but they're all ones and zeros. Okay. And it's doing with a thing called statistics. So the statistics are being applied a thing called gradient descent. Gradient descent, if you're a statistician, is the way nearly all AI and ML is done today. Why? Because it's what we know how to do. And statisticians can use gradient descent to find the lowest point or the best point on a curve. Here's the interesting thing. When they find the best point on that error curve, they don't know why. They actually don't know if it's the best point. They just keep running the circuit again to see, was there anything better? Because there's nothing to tell them it was the best point. We are going to fix that. Set theory and interval modal arithmetic will guarantee you it is the best. You could stop. Go on to the next problem. Interesting. And we've proven that. Mathematicians, first of all, proved it with set theory themselves. We've proved it with a couple of cases that I'll tell you real quick here. So that best guess in statistics is where you use the power of the computer to do things 1,000,000 times faster than you and I. You know, every computer can add and subtract. These days, most computers can multiply and divide. Some computers can do vector processing that operate, instead of on two numbers, it operates on a whole line or a curve all at once, right? Ka-chunk, one cycle, ka-chunk, another cycle that operated on that whole curve. The way I think about the way we do set theory is we operate on the whole plane, a whole plane of matrix of numbers at a time, a whole set between an interval of, call it -1 and +1. We can operate on everything in between them. Okay, that's oversimplification, but that is actually the answer. The black box that I described earlier is, all right, I showed you the 1,000th one. The computer said it's a cat. Why? Well, because it had 1,000 that weren't and 1,000 that were, so that one must be a cat. Can't tell you why though. Whiskers that curl or whatever. Purrs. So I think that's the thing, that's the worry, frankly, that a lot of people have about AI today. Because if you pick a different starting point, you'll come up with a different answer. So it's not repeatable. That's not a high level of confidence. I mean, if you come up with a different answer by just coming in with a different starting point, you would, if you were the teacher, you would say to the kid, you failed. You just tell the computer, do it again. By the way, it won't come back with that same answer. Guaranteed. It can't. So, and by the way, a lot of research time then is spent trying to figure out, what am I measuring? What am I comparing? What is the training? What is my starting point? What's my next best guess? It's a real case of the swag. So that's the reason for the diminishing returns. Our vision is to use interval modal arithmetic, set theory, which we have a lot of patents on. You can't patent arithmetic in mathematics, but we patent around that how to implement that on a computer, because no computer has ever had that instruction set. We will put that instruction set into the general purpose computer and into the vector processing algorithms of the computer. Put that then into silicon, which will make it run 1,000,000 times faster than, at least, than we're doing today. So that's where we're headed with the ASIC and to implement those patents. A couple of fundamentals here, I've covered a lot of them, but the difference between traditional AI processing and ML processing is on the right here, with the statistical processing and gradient descent. On the left is ALiX, which is the name we've given to the software that we're implementing. This team is all Minnesota-based, which is interesting. I find that also interesting because almost every supercomputer made by the United States and the world, for the most part, was actually started here in Minnesota. Control data research, SSX, ETX, and on and on. Certainly NEC and some others have tried some things and done some good things. But when you think of that history, we have a pretty proud history when it comes to supercomputers. I know that because I did one of them when I was with the IBM company. So I would say our system here with ALiX is hyperparallel. What do I mean by that? When you put two processors together to solve one problem, you would like to get twice the compute power. When you put three together, you'd like to get three. When you put 100 together, you'd like to get 100 times the compute power. That's not what happens in most parallel processing today. The reason is there's friction. And the friction is typically, I'm looking over my shoulder to say, what are you doing? Looking over my shoulder this way to say, what are you doing? And each processor is doing that shoulder tapping, and that loses some, and it could, in fact, make 1 + 1 = 1.5, not 2. Could make 100 processors, not get 100 processors of capacity. We, with our parallelism, don't have that problem. We don't get perfect, but we get a much, much higher degree of what I call hyperparallelism. Another is we will find in one run the global minimum. And we will know it's the global minimum. That's a very distinctive difference. We'll also then be able to give you an explanation, because when we run it again, restart it, we get the same answer, 2 in a row. You don't have that happen in AI, statistically based processing. So that's a couple of differences. On a simple chart here, I can show you the hyperparallelism. If you have an error curve of this is just a sample of a curve that you might have in a problem, and you've decided here's all the inputs and what they look like, and the error away from it on the right answer. Here's a case where on the this chart is one computer's working on it. This chart, we've divided it to split it between 2 computers working on it, then 4, and then 8. And if we kept going, we could have 16 or 32 or 64 processors working on it. In fact, that's what we will do with our hardware implementation. We'll have 100 cores and more working on the problem, be able to divide the problem into that many pieces, reduce the shoulder tapping, and create almost a complete core work against that process to solve the problem. So that was a problem that was called Enville's law, and back in IBM days, Gene Enville worked for actually me and IBM. So this problem goes away, and what you'd see here is the ALiX software, when dividing it up, all of a sudden realized that there is no possible answer in this segment. If I tell you how that works, I have to shoot you, so I won't tell you exactly how it works. But it knows there could be an answer in these, but there's no answer in this. So it immediately stops processing all the guessing that's going on in that interval. Back to the basics here: training, explainability, and inference are the 3 areas. We see the biggest impact on training, that we will train the system, whatever you're training it on, cancer research, space exploration, CAD/CAM design, etc. And we'll train that much faster with a definitive answer than you would get for statistical processing. Further, we're able to give you an explanation of it. I'll give you an example of this. And then what that allows you to do now is have a much lower cost inference engine. So now that you've trained the system, you can have a much smaller computer run that system and know whether or not it's a dog or cat, in my example, as opposed to a big computer that would have to have all of the data and solve that problem. So a couple of examples that prove to us, me in particular, doubting Thomas that I am, that interval modal mathematics would be revolutionary and actually worked. So we worked, and we're fortunate enough, to work with McGill University on colorectal cancer research. They had tried for some number of months, like 18, throwing a lot of computer power at it to solve a problem, and we're not able to solve the problem. And I'll give you a little bit more example on that. In 45 minutes on our computer, off-the-shelf computer running Windows, we solved the problem. We were totally blown away. So were we, to make sure that it was right. And but it was correct. We've done a similar thing with COVID, with the geometry of molecules as they studied it, and found answers much, much faster than a general purpose graphical processor. We did some pathological benchmarks, that is, things that mathematicians know the answer to, but computers can't solve too easily. And there's a number of those. And then more recently, the Space Force, and it's not a joke, the Space Force, a derivative of the Air Force, has put a couple hundred companies to select, review, and then select those that would have the most impact on automation in the future, particularly in space. We were selected as one of 10 of those, and they're courting us. We're courting them down at Sandia Labs and elsewhere to study some problems in space that we think we can solve. We definitely will need the ASIC to do it, but we're working with them closely to do it. So this disruptive approach is totally unique. The software is available, which is kind of backwards. I've rarely been involved with hardware where the hardware didn't lead the software. This is a case where the software is actually leading the hardware, because we're doing that in emulation. So it's slow, but it gets, because of that process I described briefly, it gets to the answer quickly. And it is mathematically provable. I'm not the mathematician here either. I've taken too many credits in math, but I still can't say I'm a mathematician. And this proof of both cancer research and the Space Force and COVID and the others have shown us it's real raw capabilities. We'll look for the hardware to be available sometime in second half of 24. So that's not that far away. And we'll bring that to market as rapidly as we can in 25. The difference is teraflops, 1 trillion floating point operations per second, and more of them is not always the answer. It's the only answer we have today. And it doesn't always give you the solution. As I say, statistics won't give you the best answer. And if it gave you the best answer, it doesn't know it did. That's kind of a real stinker, you know. So the parallelism is very, very efficient. And this global minimum that we do find will save, I really think one of the biggest savings here is not just computer time and cost, but researcher time. Think of how much researcher time is being hit against the wall here, like the 18 months at McGill University trying to find colorectal cancer solutions. Here's the example I'm referring to. McGill University I've been working for about 18 months using general purpose processors and high-speed computer processors. They were doing blood marker analysis. So they're taking samples of blood, a basic medical tool, running it through a mass spectrometer, coming out with a database of what are all the enzymes and proteins in that blood. Turns out there's like 1,200 to 1,800, a lot. And how do you then track that against people that have colorectal cancer, and what drug they used to treat that? They came up with nothing. 18 months, a lot of researcher time, a couple of doctors, and nothing. Estimated they spent a couple of $1 million, not counting any computer time, because the computer time was viewed as free to the researchers. We boldly asked them if we could have the data. We ran basically the raw data through the ALiX software on a Windows system. It was a little bigger than my laptop, but it was 320 core processors on a bunch of towers, about 10 different towers, each with 32 cores. So they were, racked and stacked next to each other. And the 320 cores in unison ran for 45 minutes and came up with bang. Here's the answer. These 10 enzymes would predict with definitive answer that you have colorectal cancer. Therefore, they could then use that to come up with a point of care kit rather than a very expensive mass spectrometer, lots of blood samples, and a guess. And that's where they're headed today. They quickly started a joint venture with our team to put this team in place to do a kit that could be done at your doctor's office or at home or your pharmacy. Extremely powerful, since that's a killer and often a silent killer in the medicine field. Very different story here for the space program. As I mentioned, we're part of the Space Igniter program. We're looking to work on problems here with satellite data processing, collision avoidance. There's a lot of things in space these days. Space is very, very big, but at 25,000 miles an hour, you hit something the size of your fingernail and you will do a lot of damage. Put a hole in that satellite or whatever. So they see that as a big deal. My nephew actually ran that program out of the Air Force at the time. And it's a tremendous data feeding problem, and then measuring, and then how do you intercept those things? So they're actually looking to collect garbage and park it someplace in space so it will be away from the orbits. We think we can help solve that problem for them. Another one was with COVID research. 20,000 geometrical features were identified. We were able to use the system here to rank them, explain the training accuracy, and give them answers that they hadn't been able to get. They came up with the standard processing that gave them 18 different features versus our 20,000. So a little proof there. Another one was the pathological that I mentioned. You can take an equation. This is a two-dimensional equation that would actually look like this when graphed. Try and find the low point for that graph. Think of a marble placed anywhere on that. This is the two-dimensional representation, but put a marble on any place on that graph and see where it rolls down. Well, it's going to roll to a lot of bottoms before it finds any bottom, if it does ever. We then did that in 10,000 dimensions, not 2 dimensions, and we solved the problem. So we're pretty sure we've got something here. So there's a lot of other value that we believe we bring to the market besides just performance, and besides comparing it to a teraflop, a trillion floating point operations per second, or a petaflop, 1,000 of those. We will find nonlinear optimization with a guaranteed solution, right, with less time, reducing a lot of the scope of work, as I was saying, that we throw it out, and we'll give a training method algorithm that will compress the number of new neural network layers that you need. I didn't go through that whole process, but most neural networks today have a lot of hidden layers in them. We think we can do it with just a single layer. That will greatly reduce researcher time, reduce the computer time, give you an explainable answer that's repeatable, and go from there. So where we are is we think our system will reduce the risk with a K by using a RISC with a C architecture with the ALiX software on top of that, with the interval modal arithmetic in the ASIC chip. That's where we are. So we got a team that's got a lot of gray hair, a lot of experience, a lot of doubting Thomases, and we think we can do this. We need a few funds. We're in that next gamut to either become part of that CHIP Act or some other investors that can make us do that. Let me stop here, Jason, and just say if there are any questions or follow-up, or see if we can stump the band. Yes.
So are there any training workloads that haven't achieved some of these impressive results? That's what
Yes and no, we haven't actually
real
run
quick,
any.
Tom.
Sorry.
I was just going to say, if you could repeat the question just so the people online could hear it, that would be great.
Sure. The question was, are there any training workloads that haven't worked? Basically. The answer is we haven't tried any that haven't, but we've also avoided some that we know would not. So radiology images wouldn't work for us yet because we need the chip. We would need the performance level of the chip to do it. A GRAIL application for the genome is slightly large. We wouldn't try that until we have the chip. With the chip, we think we can do that because we put enough of these chips together in a rack. We think we can hit a petaflop of capacity with on top of ALiX. some of the space stuff is definitely going to need the chip. The good news is with our training engine, we can put as big a processor as we need on the ground through the training. And as a result of that, now do with a small processor up in space, the inference. So ground will find out was it a cat or dog or a stray part running around in space. And the inference engine will be small and run in the satellite. So
Inference require the same instruction set.
no, we're not. And guys, jump up and down if I'm off base on any of this stuff. Yeah, go ahead.
So forgive my ignorance, but like.
No bad questions here.
Who is your customer, right? Are you going after, because it can be like put in Dell computers or HP or Apple, or how does that happen?
Great question. So the question, Jason, was who's our customer? And you'd like to say everybody, but it's a couple of fundamentals there. I think our early customer will be early adopters that are the actual AI scientists today, like the Accentures, the findability. Findability has done some massive work on, and they're in 3 continents in the US, Japan, and Canada. I happen to know the CEO quite well. And so we've asked him to work with us on this. Give us a stump the band question or give us a question that you've answered. And we will try and do that. I'd actually like to do some of that beginning like next month in a platform as a service offering on standard Windows computers, if you will, in a data center, in a secure site. And there's a couple of guys in the US government, I guess, to do the same thing. So, and then after that, so I think they'll be the early adopters and they'll be the credibility test maybe that we need in the industry. There's also a thing called ML-perfs. ML-perfs is a standard industry benchmarks for AI computing. NVIDIA has a template on that. And so, how many teraflops solves this problem, if you will. That'll be the first thing we do once we have the system and the hardware and do a comparison with and without interval modal arithmetic instruction set and do a comparison. So we'll brag about that as soon as we can. The next part of your answer is the cloud users, AWS, Microsoft Azure, IBM, Google, among others, are the largest users of AI today. ChatGPT notwithstanding, but lots of other stuff too. They rented everything from by the year, by the month, by the hour today. And they'll give you as much capacity as you can take and spend. So we will see them wanting our system, we think. The balance there is they may change their pricing algorithm because like most early computer things, you do more for less and you have to make it up on revenue. So how do you do that? So I've been down that route once or twice. So I think I might be able to help them do that. The third is the systems houses. Then the systems houses, Dell will probably want to white label it, whether it be Dell or IBM or HP, to pick 3, and white label it. Then the last I would say are the systems houses for software. The SAPs of the world, the Oracles of the world are slightly large users of customer enterprise data. Much of that is, I think even today, 70% of that is still viewed as running on the mainframe, believe it or not. So we think they'll want to combination package it with their solutions as they get broader and deeper into the marketplace. So you take an Epic for hospitals or a Cencor for surgeries or for the old JD Edwards stuff for the enterprise back office. And as they start to move that towards more AI modeling. The retailers, I mentioned, as you came in earlier, the Walmarts and I can guarantee it, Walmarts and Targets and others have a massive amount of information today that they're spinning the wheels on to do logistics for inventory, do pricing for sensitivity analysis, do where is it? Because Tom wants to buy one and it's not in this store, but maybe it's in the one down the block. How do I know what to order, back order? How do I tell you what it is that's in what aisle as you're walking down? How do you say it in your phone? Where does it point me to it? All of that stuff is a vast array of information from the UPC codes to the QR codes that to marketing to one. I think that's where it's headed. I know a little bit about that, having run that business for a number of years. That answer your question? Yeah. And if you know anybody else that wants one, we'll sell it. Yes, sir.
My apologies, I couldn't get here at the beginning because of other commitments. So I missed most of your presentation, but I saw some reference to space. I'm assuming you have AI deployed at the edge, right? Because without that, there is no cloud connectivity in the space. So how does that work, right? Is it edge AI kind of application?
So yes or no? I mentioned that the training is likely to be done on the ground in a computer data center. Then the result of that training, you have an answer, an explained answer, and then you'll be able to put that into the inference engine, which can be at the edge then.
Okay.
We'll probably play in all those over time, but the key at the beginning will be to play at the ground.
Okay.
Where we'll start out in those data centers, whether it be an enterprise data center, the cloud data center, a government secret data center, or whatever else. Does that answer your question?
Yeah.
And so as a result, the inference engine in the satellite will be much smaller than would normally have been, much lower power. I think those are two good things in space.
I've worked with many organizations in healthcare and life sciences in my previous role. Was with Microsoft. Just exited 4 weeks, 5 weeks ago, but there was a lot of interest from healthcare systems to have AI deployed at the edge, and that's the reason why I asked this question.
Yeah.
Because there might be some significant opportunities.
Well, I think there's definitely, I invented with a team, a smart clean cube operating room. And I won't go into the details of that, but it's installed now in places and it is gathering information at a very rapid pace. What I realized in doing that was no one was gathering all the information for the room. Every patient, every procedure, every surgical team, every piece of instrumentation, every piece of equipment, what the humidity, temperature index was, what the plume of smoke was that's coming from the cauterization was all not getting measured. Or any place it was measured, it was stovepiped by the provider of that piece of equipment. And by the way, they weren't sharing any of that information. So we've taken RFID and IoT and connected everything. We have massive amount of data that's going to come out of every single surgery. So when Tom has his knee operated on, it will not only be the cleanest room in the world, he'll have more information out of that coming to that, and so will the surgeon. So it'll be a continuous learning process. And that's what my focus is. Continuing learning process, because why does Tommy do surgery in 3 hours and Sally does it in 2? Is it their training? Is it their age? Is it their what? And there may be good reason, particularly if the results are the same. Good, but let's know. Yes, sir.
Now, when I what the instruction set, modal interval, does that coexist then with the traditional instruction set on the RISC backbone so that you can perform standard functions along with the actual customized set? Is that?
Yeah, that's a good question. So our expectations will put it, the answer is yes, very simply. So the question was,
You don't have to replicate all the standard things.
no, we don't. So the question is, will the interval modal arithmetic instruction set coexist on the with the standard instruction set? And the answer is yes. We believe that may be redundant over time, but so be it. You
Well,
got
a sub-theory or a category theory beyond that, right?
Right.
You have to replicate all of the logic for it, and any kind of should be in place today.
right,
That on quantum, right? You want to put that on.
exactly. We don't need to take that on.
RISC is open source, right? Or it's like an open source. So how are you using your patents really stuff for that?
Well, we'll put it in silicon. That's one thing. Once it's in silicon, it's a little harder to figure it out. There'll be, tens of millions of transistors, resistors, capacitors on a silicon chip on a wafer, et cetera. That's a little harder to crack than the software. The ALiX software will still be running on that. and using those instruction sets. So there'll be about 30 instructions on the vector processor. There'll be about 30 instructions added to the general purpose processor. And that combination, when invoked by ALiX, will do the interval modal arithmetic that I was describing. We have it patented, so the IT industry has been pretty good with patents. I've stumbled around places that haven't been pretty good with it. So we know something about that. We've also got some trade secrets into that implementation. So we'll try and control the developers who are helping us to do this, because we won't do it all in-house. We'll be able to use the Global Foundry, for instance, to do the fabrication. We'll have some electronic design team work with us, and they'll be under contract and security to do it with us. You do the best you can to protect the asset you have.
And
James?
also, we're going to license the RISC-V core. We could develop it ourselves, but to get the market quicker, there's plenty of RISC-V core processors developed, the vector processing, so we're talking to several vendors.
Yes, sir.
Consider ARM, are you an alternative?
They considered ARM. I wasn't party to all the considerations that were part of ARM, so you'd probably get a better explanation from one of the guys. But RISC-V clearly was designed to have modification to instruction set. And that was the defining difference, right? Just plain and simple. Yeah, it was made for, oh, you want that? You can do that. That's not true of an x86. It's not true of ARM at all. So, if you want to break into those, that's breaking into Fort Knox today. And that's not a good idea. And I've knocked on the doors of the big guys. I've been one of the big guys, and I know a hell no answer.
These are more like grandchildren development.
So it's so RISC-V was designed, if you don't know, RISC-V was designed with that in mind, a customized instruction sets to be baked into the silicon of that architecture. And that's a fundamental difference from virtually any, certainly ARM and x86 and the GPUs of NVIDIA. Think about when the x86 came out. Most of you are too young to know that, but it came out 80, 81, 82, in that time frame. That's 100 years ago in IT time, and it is still the core architecture. When did the 360, 370 architecture come out? Before that, it is still the core architecture of the mainframe team that I ran. And it is closed. It's a closed architecture. You cannot put another instruction in it if you tried. That's a defining difference that controls this industry, which, I'm on the other side of the desk now. We're leveraging those changes to this industry. And you've noticed a couple of big guys saying the same thing. Microsoft and Google have said they're committing everything to RISC-V. They won't get there tomorrow, but that's a big wallet. Yes, sir.
Please understand more as understand process and how that's the original. We have a processor dealing with memory. In your case, it's memory. You get people processing your environment, and then the result is an input.
No, the modal arithmetic goes on in the process part, right? It's part of the vector processing and part of the general purpose processor. So it's an addition to the additional structure set.
That's exactly what I'm trying to understand.
Add, subtract, multiply, divide,
That's what this thing.
add modal, add, subtract modal.
That's a little bit different.
Okay.
So I'm trying to understand practicality. So I'm dealing with multiple models. Heuristic model, multiple models. I'm using Someone is working on all that stuff. The process is, when we get the data, we can then implement model processor. And this will help us more, and I think that. So
Bob, you wanna,
in my daily life, your processor is supposed to help me with accumulating trading price of things. Then the way that I have a,
correct.
and, so I will.
Well, ALiX software is going to be sitting on top of that operating system, right? Go ahead. Yeah, please.
So you deal with, models, there's a whole bunch of them. And different models are good for different kinds of problems. You might start with one model, you try it on the problem, and that's not going to work. Then you try another. You might do some mini models before you find one, and what's not works. Those models, you can do any for example, and you can train it with AI. 3% AI, and you get something. With modal ALiX, you don't need to have those models. You can use them if you want to. But with those models, you may have several hidden layers in between. And ALiX doesn't require several hidden layers in between. Mathematically, if you're improving that you only need one hidden layer.
That's my basic. I'm an electrical engineer, I understand it's impossible.
On this chip versus the application, right, that everybody's comfortable with as an XC, right, and as brain identification capabilities. How do you know the application is separated from the chip? Okay, so at least to talk about it.
So you start with the data, you put the data in, you have to have a model, right?
And I have a variety of data, listening data, image data, and database.
You get all kinds of data, you have a model for each kind of data. For the data.
No, yes, my goal is I have a data, a variety of data. Database, my linguistics, and my English, see, I work with a nice scheme for it. That's not all images out there. Or I have a linguistic theory of intent. I need to buy a car, and then problems, a variety of different data. And I want to create a model which I then can use applying to my people. So I have so with the model I can do that, and this is one of the ways, using lots of models, and that's what it's my creating multiple models apply to different variety of data sources as models. So it's helpful to you.
Just for Jason and everybody else listening, they're asking about what is the model and how do you input a model with modal arithmetic versus standard. Is that fair?
It's a model, it's not standard. It's a variety of models. ChatGPT has one kind of models.
Yes.
Large language models. I don't use large language models. I use a different model, but still models.
So the reason we're already absence of the word algorithm in this entire dialogue, right? Because I think that's what's missing, right? How does the ALiX chip, right? It's a physical thing, right? That has circuits and transistors and all that stuff, right? And then it runs a Linux operating system, and then you run that in this modal arithmetic manner to then build a model, right? Or set of models. What's the algorithmic interpretation?
You start with, you've already got your data, you've already got your models. You know how to run those in radian descent. You have to get those into your computer now. And there's different standards for having a model and the data going to your computer. NNEF is one of them. You familiar with NNEF? There's a whole bunch of different models.
NNEF and Onyx are two of the biggest models where you input their transforms. So you input your data or whatever TensorFlow data sets that you have into one of those. We have embedded NNEF inside of ALiX. So that can accept what we think are the pervasive data models that are out there today. Does that help?
If I understand it correctly, what you are asking for, the answer is probably that there is a software component. I'm using mere model language, okay? So
yeah.
Pardon me, I'm not using, but there is a software component and there is a chip component here and execution environment. Right? The way it is hardware. Right. So the hardware component is what you are referring to. How do you use it on that? I understand it correctly. That's it.
Okay, from the schedule, I'm wanting later.
Let me ask you this, when you ran that demo, for the colorectal cancer, you said you were running on Windows. Were you using this thing as a sub-processing unit, and you would GPU or some other?
It actually looked like a large Excel data sheet being fed into ALiX.
How did your computer run Windows? ALiX isn't running.
We have an emulator,
Windows.
because we have an emulator that emulates that chip instruction set.
Yeah.
Okay, so instead of doing normal computer arithmetic, we did interval modal arithmetic with the emulator.
So if I was going to test, if I thought about this thing as talking to a DSP, would that be a fair, crude comparison?
Crude.
Yeah. But that's basically.
I don't know if it's fair, but it's crude.
But I'm not running the environment that you're actually doing the work and the UX and all of that.
No.
I'm not running that chip,
No,
right? It's a slave, I guess, it's a sort of.
And we can introduce this. It's a skill model based. It's making it faster, better, but still.
But here it's not appealing to many of the algorithmic techniques people find in a lot of classical analysis ways, which is the subgroup process, which is considered.
so I think we can take some more of that off.
Yeah.
If you want. I wanted to
Yeah,
take a
if I could interject here, maybe let's, why don't you guys let you talk more about offline. We did have a question here speaking. I think you guys were talking about GPT-4 at one point, but Rolf had a question. If you know how long it would, how long ALiX would take to reproduce GPT-4 when the ASIC is functioning? Have you guys thought about that with regards to?
That's we've thought about that. I don't have an answer for you, you know.
Yeah.
It will probably run a while, but however, we think the large language model that uses can be then applied with ALiX to the interval modal arithmetic once we have that chip. And then we would gang together a whole bunch of those chips, a whole bunch of cores. You tell me how many cores you got, you know, the GPT-4, I think has, I don't know how many cores Microsoft has running on that right now, but I'll bet it's a bunch, right? You tell me how many and I'll tell you that we'll run faster, we think. I got to prove it.
Yeah, and you've done the calculation, because this follow-up question was how much energy would it take relative to current GPUs? You guys wouldn't know that, I guess, as a fraction of current GPU energy usage.
Yeah, I think there's two answers to that. One is because it's going to be more efficient, it'll run less time, therefore less computer power, therefore a hell of a lot less energy, right? Think of how many teraflops were being run for 18 months by McGill with no answer versus 45 minutes, which cost us 4 cents, literally. I think it was a little more than 4 cents over 18 months of just energy power, right? So I don't know, that's not a good barometer either, but it's it's the only crude one I can give you. Then the additional one would be the quasi-adiabatic added to that will run less energy for every cycle used. And we think that's in the range of 50% or better. That answer your question?
Yeah, I think so. That's excellent.
That's all I can give you.
That's
We
good.
have a
Any
question
other?
in the back of the room here, Jason. Yeah.
Go for it.
Sounded less like typical things like they're about AI, the bias towards the model stuff that is in the current. But more around emulation concerns. Content to a certain thing is the optimal. Is this purely an AI application, or does it have this broad applicability to things like mix, optimization, phase like that?
I would put it under the law. The question is this traditional or is this specific to AI versus a more general purpose utilization? And I would put it under the umbrella of high performance computing. So any place you've got high performance computing, we should be able to apply this. Nonlinear optimization is a key area of improvement, right? And that always falls to the case in AI and global minimums. It may or may not fall into the case of other places, but I'll give you, for instance, Quam with that kind of communications, circuit design. That's not AI, although guys doing it sometimes think it is AI. It's going to apply there too. Do you guys want to add to that?
Yeah, the invention is basically a nonlinear optimization problem solver. Guarantees you can solve nonlinear optimization problem. That's a fundamental thing.
And the heart of it is a new method for solving certain mathematical problems. Around nonlinear optimization. Right, it's simply a nonlinear optimization problem.
So this is one targeted application by the set theory, the set theory formulas. All right, so just very briefly, I'll point out that there's a really great mathematical physicist named John Baez, based out of UC Irvine, who I used to follow postally on Twitter until Musk screwed it up. And now I can't see the guy very much anymore, but that guy has spent the last several years showing all the different ways category theory can be applied to then provide all the quantum mechanical, quantum field theory things we know, and a whole bunch of other stuff related to fundamental foundation of physics. So you could rewrite everything we do in logic, relationships, and all that stuff, starting from that point of view. You could rewrite the entire risk construction set with this stuff if you wanted to, but you're not doing that. You're making this one application that could be this problem solving.
Happens to be a pretty large application.
The inventor started with video rendering. It was having trouble with the calculations for doing video rendering. That's where it came across a little bit. Many applications, but.
So that whole image processing is an area, rendering.
Another quick question about, do you have competition right now? Is there a feeling like you have to move quickly or any of that?
But I'm the most impatient guy in the room, so I think we got to move quickly for starters. But to your point, the world is moving very fast, so we don't know precisely where it's going to be in 2 years, and we're clicking off here. But I think we can anticipate that with lots of prognostications of our own and others. But I think NVIDIA and Intel are leading the parade in this today, with AI processing and others, AMD as well. But and billions are being spent every month on solving this. I think the current estimate is it's over $165 billion just on the core stuff to hardware to run that. So we want to get into that game. That's for starters. And the longer we wait, the difference changes. We think we've got a fundamental difference though, right? And so no one is doing interval modal arithmetic in hardware on the planet that we're aware of. There are some people doing interval arithmetic. We've encountered those in the Space Force.
I think Wolf uses it.
Pardon me?
Wolf uses it in their deep
What was interesting, they weren't using interval modal arithmetic. And that's the difference. Another way to think about that is modal arithmetic was proven and solved by some scientists out of Spain. And if classical interval arithmetic handles positive numbers, but it doesn't handle all the negative numbers or infinity or zero. Other than that, it was really good. We do handle all of that. Negative numbers, zero, and infinity.
Two additional answers. One, I think I have lots of customers spending lots of money on RISC, and I don't want to put that off any further than I have to. And two, with the results that we had at McGill, this will save them on lives. And I don't know whose life it might save, but I'd like it to happen as soon as possible. And there's a huge benefit for everybody in that aspect, and I think it's going to put society in a very ways. Just going to help the world keep you saving them.
My daughter is part of a group that runs the Minnesota colorectal cancer research group. She's you hope you never need her. She's the specialist in hematology, oncology, and transplant. Long story short, they run a money raiser every year. What their theme was this past year was time. And I believe that's what we are going to give. We're going to give researchers more time right at the very beginning. We're going to use less computer time. We're going to give, most importantly, the doctor and the patient time to treat it. Because I'll give you, for instance, in colorectal cancer research, they won't even start to treat you until one of the characteristics exceeds 1,000. With what we discovered at McGill, we'll know if you have it at 50, so they can start treating you way earlier than they were before. And instead of having to go through $1 million mass spectrometer that's not in your local pharmacy or your local doctor's office, we'll have a test kit that's this big that says, go try it, get the answer. So that's time for the patient to get treated earlier, time for the patient to get cured faster, time for the researcher and the doctor to get an answer better. I think that's the value equation that we're after. Pardon me?
Who pays for that then? I'm sorry, I'm asking.
Yeah, no, and actually, I want to get a piece of that value curve. And I'm working on it. I'm working on it. We don't have a clean answer to that, but the ALiX explanation, by the way, that software called the Explain, different than ALiX, will be charged. So if ALiX costs you $1, that might cost you 10.
So if I build on her question, what are your intake criteria right now? Have you started commercializing process? Or tomorrow, let's say, if there's a customer, quote unquote, who wants to get started on this journey with you?
Yeah, good question. So the question, Jason, was
This will have to be the last question we have.
okay. Send money and we'll start with you. Maybe is the simple answer, but what's the input process for us to get started with someone? The simple answer is I'd like to set up a platform as a service as soon as I can to start running this with my Windows system to start getting values like more McGills. Okay, because blood marker research is very prevalent, and also answers to it are very bad, as we saw. So I'd like to get more of those in pharma, by the way, as well as in life sciences, as well as other ones. So that's one thing. What I don't want to do is subtract from us getting to the goal of the hardware and software implementation with the modal arithmetic. So it's a balancing act of getting some of those early adopters like McGill or like Findability and others. But I do want to get maybe a handful, a dozen. So if you got one or you got an idea, I'll give you one shot. One free shot.
Well, that's good. In fact, I encourage you guys to continue to talk in the room and continue to ask questions, and you guys can stay here at Lab 651 all night. But I want to be respectful of the time of the people that are online here. So thank you so much, Tom, for the great presentation. I guess I encourage people who are online, if they could, if they want to show up in person the next time, it's a much more rich experience, I guess. So maybe that's a little bit of a way to encourage people to come on down, get out in person, and be able to meet up with our group in person and network. But I'm going to shut down the online Zoom meeting. I know our group here will continue to ask questions and keep moving on, but I want to thank you so much, Tom, for coming to our Applied AI meetup, sharing all the awesome things you guys have going on at RISC. And sounds like you're just right on the cusp of actually doing some very, very cool stuff. And so can't wait to see what happens here in the next 6 to 9 months. So good luck.
Thanks so much for the opportunity.
Thank you. All right. Take care, everyone online. We'll see you next month. We will be back on July 6th. Take care.